The grounding detail raised concerns because it was unclear. The purpose of the 4/0 grounding conductor in the metal raceway and the bonding bushing bonding jumper was not specified in sufficient detail. The 4 American wire gauge equipment grounding conductor, or EC, was not shown connected to the equipment grounding bus on the rooftop. The bonding jumper size was not specified, so let's delve into the applicable codes and standards. National Electrical Code, or NEC, Section 800.48 addresses isolated grounding systems and requires the isolation of the grounding system for cell antenna installations from the building grounding system. NEC Section 250.106 requires that all equipment grounding conductors be connected to the grounding system. NEC Section 250.60 requires that grounding electrodes be bonded together to form a common grounding system. NEC Section 250.58 specifies the minimum size of bonding jumpers. Now let's consider some possible interpretations. The 4/0 grounding conductor could be intended for lightning protection. However, this should be clearly indicated on the drawings. As per NEC Section 250.58, the bonding jumper size should be equal to the largest equipment grounding conductor connected to the bus. In this case, if the largest equipment grounding conductor is 4/0 American wire gauge, then the bonding jumper should be sized accordingly. The NEC requires that the grounding system for cell antenna installations be isolated from the building grounding system. This means that there should be no direct connection between the equipment grounding conductors for the cell equipment and the building grounding system. The isolated grounding system should consist of a grounding bus, grounding electrodes, and bonding jumpers. Here are some key recommendations. Contact the engineer to clarify the intent of the grounding design. Confirm that the 4 American wire gauge equipment grounding conductor is connected to the isolated grounding system on the rooftop. Ensure that the bonding jumper size is appropriate as per NEC Section 250.58. Review the existing service equipment to determine how it is grounded and if it meets the requirements for isolated grounding systems. Now let's delve into grounding conductors in a more detailed manner. Grounding conductors serve a critical role in electrical safety by providing a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices like circuit breakers or fuses. This process helps to minimize the risk of electrical shock and equipment damage during fault conditions. Grounding conductors can be categorized into several types, each serving a specific purpose. Firstly, there are equipment grounding conductors, or ECs, which connect the non-current carrying metal parts of equipment, such as enclosures and raceways, to the grounding system. Their primary function is to provide a path for fault current to return to the source. Secondly, there are grounding electrode conductors, or GECs, which connect the grounding electrode system to the service equipment or separately derived systems. These conductors ensure that the entire electrical system is effectively grounded to the earth. Thirdly, bonding jumpers are used to connect different parts of the grounding system together, such as metal raceways, enclosures, and equipment. These jumpers maintain electrical continuity and provide a low impedance path for fault current. The selection and installation of grounding conductors must adhere to the requirements of the National Electrical Code, or NEC. The NEC specifies the minimum size of grounding conductors based on the size of the ungrounded conductors in the circuit. For example, NEC Table 250.122 provides guidelines for sizing equipment grounding conductors, while NEC Table 250.66 provides guidelines for sizing grounding electrode conductors. Grounding electrodes are conductive objects that are buried in the earth and connected to the grounding system. They provide a direct connection to the earth, helping to stabilize voltage and provide a path for fault current. Common types of grounding electrodes include metal water pipes, ground rods, and concrete encased electrodes. Metal water pipes, when used as grounding electrodes, must meet specific requirements outlined in NEC Section 250.52. The pipe must be in direct contact with the earth for at least 10 feet, and supplemental electrodes are often required to ensure effective grounding. Ground rods are typically made of copper or copper-clad steel and are driven into the earth to a depth of at least 8 feet. The NEC specifies the minimum diameter of ground rods, as well as requirements for spacing and installation. Concrete encased electrodes, also known as UFA grounds, consist of a bare copper conductor encased in concrete near the bottom of a foundation or footing. These electrodes provide a very effective grounding path due to the large surface area in contact with the earth. Bonding is the process of connecting different metal parts of the electrical system together to create a continuous electrical path. Bonding helps to minimize voltage differences between metal parts, reducing the risk of electrical shock and ensuring that fault current can flow effectively. Bonding can be achieved using various methods, including bonding jumpers, bonding screws, and bonding bushings. Bonding jumpers are used to connect metal raceways, enclosures, and equipment together. They must be sized appropriately based on the size of the circuit conductors and must be securely attached to the metal parts being bonded. Bonding screws are used to connect equipment grounding conductors to metal enclosures. These screws must be identified for grounding purposes and must be installed in accordance with the manufacturer's instructions. Bonding bushings are used to bond metal conduit to enclosures. They provide a low impedance path for fault current and help to maintain electrical continuity. Isolated grounding systems are used in sensitive electronic equipment installations to minimize electrical noise and interference. In an isolated grounding system, the equipment grounding conductor is isolated from the building grounding system. This prevents noise current from circulating through the equipment grounding system, which can disrupt the operation of sensitive electronic equipment. The NEC provides specific requirements for isolated grounding systems in Section 250.146. These requirements include the use of an isolated grounding conductor run with the circuit conductors and the installation of an isolated grounding receptacle. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning, utility switching, or other transient events. SPD diverts surge current away from sensitive equipment, preventing damage and ensuring reliable operation. SPD are typically installed at the service entrance and at branch panel boards to provide comprehensive surge protection. The selection and installation of SPD must comply with the requirements of NEC Section 285. The NEC specifies the types of SPD that are permitted for use in different applications, as well as requirements for installation and wiring. Maintenance and testing of grounding systems are essential to ensure their continued effectiveness. Regular inspections should be conducted to identify any signs of corrosion, damage, or loose connections. Grounding electrode resistance testing should be performed periodically to verify that the grounding system is providing an adequate path to ground. The results of these tests should be documented and any necessary repairs or upgrades should be performed promptly. When working on grounding systems, it is important to follow safe work practices to prevent electrical shock and other hazards. Always de-energize the circuit before working on grounding conductors or electrodes. Use appropriate personal protective equipment, such as rubber gloves and safety glasses. Follow lockout/tagout procedures to ensure that the circuit remains energized while you are working on it. Understanding the principles of grounding and bonding is essential for ensuring electrical safety and protecting equipment from damage. By following the requirements of the NEC and implementing best practices for grounding and bonding, you can create a safe and reliable electrical system. Now, let's address some specific points related to your situation. Firstly, regarding the 4/0 grounding conductor, it is crucial to determine its intended purpose. If it's meant for lightning protection, it should be clearly labeled in the drawings. Additionally, verify that it is connected to a dedicated lightning protection system as per the relevant standards. Secondly, the bonding jumper size is a critical aspect of grounding. NEC Section 250.58 mandates that the bonding jumper size should match the largest equipment grounding conductor connected to the grounding bus. This ensures a low impedance path for fault current. If the largest equipment grounding conductor is 4/0 American wire gauge, the bonding jumper must be sized accordingly. Thirdly, isolated grounding systems are essential for sensitive electronic equipment like cell antenna installations. These systems prevent unwanted noise currents from interfering with equipment operation. Ensure that the equipment grounding conductors for the cell equipment are isolated from the building's grounding system. This isolation typically involves a dedicated grounding bus, grounding electrodes, and bonding jumpers. Fourthly, to gain a comprehensive understanding of the grounding setup, review the existing service equipment. This review will help determine how it is grounded and whether it meets the requirements for isolated grounding systems. This step is crucial to ensure compatibility and compliance. Fifthly, remember that NEC Section 800.40 specifically addresses grounding requirements for communications systems, including cell antenna installation. This section often requires the communications grounding system to be separate from the building's grounding system to minimize interference and ensure proper operation. Sixthly, when working on grounding systems, prioritize safety. Always to energize the circuits, use appropriate personal protective equipment such as gloves and eye protection, and follow lockout-tagout procedures. Safety is paramount. Seventhly, documentation is key. Maintain accurate records of all grounding system components, including conductor sizes, electrode types, and bonding methods. These records are valuable for future maintenance and troubleshooting. Eighthly, if you encounter any uncertainties or discrepancies in the grounding design, consult with a qualified electrical engineer. Their expertise can help ensure that the grounding system meets all applicable codes and standards. Ninthly, grounding systems are not static. They require periodic inspection and maintenance to ensure their continued effectiveness. Schedule regular inspections to check for corrosion, loose connections, and other issues. Tenthly, keep in mind that grounding is not just about safety, it also plays a crucial role in equipment reliability and performance. A well-designed and properly installed grounding system can minimize electrical noise, prevent equipment malfunctions, and extend the lifespan of electrical and electronic devices. In summary, grounding is a multifaceted and essential aspect of electrical systems. A clear understanding of grounding principles, compliance with NEC, and adherence to safe work practices are all vital for ensuring electrical safety, equipment reliability, and system performance. Always prioritize safety and seek expert guidance when needed. Let's explore some additional points to further enhance your understanding. Firstly, the purpose of the metal raceway enclosing the 4/0 grounding conductor is to provide physical protection and a low impedance path for fault current. However, it's important to ensure that the raceway itself is properly bonded to the grounding system to maintain electrical continuity. Secondly, consider the impact of soil resistivity on the effectiveness of grounding electrodes. Soil resistivity is a measure of how well the soil conducts electricity, and it can vary significantly depending on factors such as moisture content, temperature, and soil composition. High soil resistivity can reduce the effectiveness of grounding electrodes, so it's important to select appropriate electrode types and installation methods to minimize this effect. Thirdly, be aware of the potential for stray voltage in grounding systems. Stray voltage is a low-level voltage that can appear on grounded metal surfaces due to various factors such as unbalanced loads, inductive coupling, and ground faults. Stray voltage can pose a shock hazard to people and animals, so it's important to identify and mitigate sources of stray voltage in grounding systems. Fourthly, understand the role of equipotential planes in grounding systems. An equipotential plane is a conductive surface that is bonded to the grounding system to minimize voltage differences between different points on the surface. Equipotential planes are often used in areas where sensitive electronic equipment is installed to provide a stable and noise-free grounding environment. Fifthly, consider the use of supplemental grounding electrodes to improve the effectiveness of grounding systems. Supplemental electrodes can be used to reduce the overall resistance to ground and provide a more robust grounding path. Common types of supplemental electrodes include ground rods, ground plates, and chemical grounding electrodes. Sixthly, be aware of the potential for galvanic corrosion in grounding systems. Galvanic corrosion occurs when two dissimilar metals are in electrical contact in the presence of an electrolyte, such as moisture or soil. The more active metal will corrode, while the more noble metal will be protected. To prevent galvanic corrosion, it's important to select compatible materials for grounding system components and to isolate dissimilar metals where possible. Seventhly, understand the role of ground fault circuit interrupters, or GFCIs, in protecting people from electrical shock. GFCIs are designed to detect small amounts of current leakage to ground and to quickly interrupt the circuit, preventing electrical shock. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electrical shock. Eighthly, consider the use of surge protective devices, or SPDs, to protect electrical equipment from voltage surges caused by lightning, utility switching, or other transient events. SPD diverts surge current away from sensitive equipment, preventing damage and ensuring reliable operation. SPD are typically installed at the service entrance and at branch panel boards to provide comprehensive surge protection. Ninthly, be aware of the potential for harmonics in electrical systems. Harmonics are non-sinusoidal currents and voltages that can distort the waveform and cause problems such as overheating, equipment malfunction, and increased energy consumption. Grounding systems can play a role in mitigating the effects of harmonics by providing a low impedance path for harmonic currents to flow. Tenthly, consider the impact of electromagnetic interference, or EMI, on electrical systems. EMI is unwanted electrical noise that can disrupt the operation of sensitive electronic equipment. Grounding systems can play a role in reducing EMI by providing a shield against electromagnetic radiation and by providing a low impedance path for noise currents to flow. Let's add even more details to further your understanding. Firstly, the size and type of grounding electrode conductor, or GEC, is determined by NEC Table 250.66 based on the size of the service entrance conductors. Ensure the GC is appropriately sized to handle potential fault currents. Secondly, when using metal water pipes as grounding electrodes, ensure they are in direct contact with the earth for at least 10 feet and supplement them with additional electrodes as required by NEC Section 250.53 D2. Thirdly, ground rods must be at least 8 feet long and driven into the earth. Spacing between ground rods should be at least equal to the length of the rod, as per NEC Section 250.53b. Fourthly, concrete encased electrodes, or U for ground, should be at least 20 feet of bare copper conductor, size no smaller than 4 American wire gauge, encased in concrete within the bottom of a foundation or footing, as per NEC Section 250.52a3. Fifthly, bonding jumpers used to connect metal raceways and enclosures should be sized according to NEC Table 250.102, based on the size of the circuit conductors within the raceway or enclosure. Sixthly, ensure that all bonding connections are made with listed connectors and fittings, properly tightened to ensure a low impedance connection. Seventhly, isolated grounding receptacles must be identified by an orange triangle on their face, as per NEC Section 406.3d. The grounding terminal of an isolated grounding receptacle is insulated from the receptacle mounting means. Eighthly, surge protective devices, or SPDs, should be selected based on the voltage and current requirements of the equipment being protected, as well as the expected surge environment. Install SPD as close as possible to the equipment being protected for maximum effectiveness. Ninthly, perform regular ground impedance testing to verify the effectiveness of the grounding system. Use a ground impedance tester to measure the resistance between the grounding electrode and remote earth. Tenthly, document all grounding system components, including conductor sizes, electrode types, bonding methods, and test results. Keep this documentation readily available for future reference and maintenance. Consider these additional factors to deepen your understanding. Firstly, soil composition significantly affects grounding effectiveness. Sandy soils tend to have higher resistivity than clay soils. Conduct soil resistivity tests to determine the best location for grounding electrodes. Secondly, the depth at which grounding electrodes are buried can also affect their performance. Burying electrodes deeper can help to reach more conductive soil layers. Thirdly, when using multiple grounding electrodes, connect them in a parallel configuration to reduce the overall resistance to ground. Fourthly, consider using chemical grounding electrodes in areas with poor soil conductivity. Chemical electrodes contain chemicals that leach into the surrounding soil, improving its conductivity and reducing ground resistance. Fifthly, when installing grounding electrodes near underground utilities, exercise caution to avoid damaging the utilities. Contact the local utility companies before digging to locate any underground lines. Sixthly, regularly inspect grounding connections for corrosion. Clean and tighten connections as needed to ensure a low impedance path to ground. Seventhly, protect grounding conductors from physical damage. Run conductors in conduit or other protective raceways where they are exposed to mechanical stress. Eighthly, when working on electrical systems, always use a properly calibrated multimeter to verify that circuits are de-energized before working on them. Ninthly, follow all applicable safety regulations and guidelines when working on electrical systems. Wear appropriate personal protective equipment such as gloves, safety glasses, and arc flash rated clothing. Tenthly, never work alone on electrical systems. Always have a qualified person present to assist you in case of an emergency. Let's consider some advanced concepts to further your knowledge. Firstly, understand the concept of transient voltage surge suppression, or TVSS. TVSS devices, also known as surge protective devices, or SPDs, are designed to protect electrical equipment from voltage spikes caused by lightning, utility switching, or other transient events. Secondly, learn about the different types of SPD and their applications. SPD are available in various configurations, including hardwired units, plug-in units, and panel mount units. Select the appropriate SPD for the specific application and voltage requirements. Thirdly, understand the importance of coordinating SPD throughout the electrical system. SPD should be coordinated to ensure that the surge energy is properly diverted and attenuated, preventing damage to sensitive equipment. Fourthly, learn about the different types of grounding systems, including solidly grounded systems, impedance grounded systems, and ungrounded systems. Each type of grounding system has its own advantages and disadvantages, depending on the application. Fifthly, understand the concept of ground potential rise, or GPR. GPR occurs when a large fault current flows through the grounding system, causing a voltage rise at the grounding electrode. This voltage rise can pose a safety hazard to people and equipment in the vicinity of the grounding electrode. Sixthly, learn about the methods for mitigating GPR, such as using equipotential grounding systems and installing surge arresters. Seventhly, understand the concept of electromagnetic compatibility, or EMC. EMC refers to the ability of electrical equipment to function properly in its intended electromagnetic environment without causing interference to other equipment. Eighthly, learn about the methods for achieving EMC, such as using shielded cables, filters, and grounding techniques. Ninthly, understand the role of grounding in reducing electromagnetic interference, or EMI. Grounding can help to reduce EMI by providing a low impedance path for noise currents to flow back to the source, preventing them from radiating into the surrounding environment. Tenthly, learn about the different types of grounding electrodes used in high-frequency applications, such as radio frequency, or RF, grounds and counterpoise grounds. These types of grounding electrodes are designed to provide a low impedance path to ground at high frequencies. Here are more points to consider. Firstly, the NEC provides specific requirements for grounding electrode systems in section 250.50. These requirements vary depending on the type of system and the type of electrodes used. Secondly, when installing grounding electrodes, ensure that they are accessible for inspection and maintenance. Do not bury electrodes under concrete or asphalt unless they are specifically designed for that purpose. Thirdly, regularly inspect grounding connections for tightness and corrosion. Tighten connections as needed to ensure a low impedance path to ground. Fourthly, protect grounding conductors from physical damage. Run conductors in conduit or other protective raceways where they are exposed to mechanical stress. Fifthly, when working on electrical systems, always use a properly calibrated multimeter to verify that circuits are de-energized before working on them. Sixthly, follow all applicable safety regulations and guidelines when working on electrical systems. Wear appropriate personal protective equipment, such as gloves, safety glasses, and arc flash-rated clothing. Seventhly, never work alone on electrical systems. Always have a qualified person present to assist you in case of an emergency. Eighthly, if you are unsure about any aspect of grounding or electrical safety, consult with a qualified electrician or electrical engineer. Ninthly, continuous learning is essential for staying up to date on the latest codes, standards, and best practices for grounding and electrical safety. Attend training courses, read industry publications, and participate in professional organizations to enhance your knowledge and skills. Tenthly, remember that grounding is not just about safety, it's also about reliability and performance. A well-designed and properly installed grounding system can improve the performance of electrical equipment, reduce downtime, and extend the lifespan of electrical systems.